Okay, good morning everyone who is joining us on this morning's reactor session. This morning's session is on big problems with big data, managing risks in AI. So we're delighted this morning to have John McClune with us delivering today's session. John is the Director of Technical Services, Community and Strategy at Wolfram Research Europe. So I'm really excited to have John with us this morning for this 1 hour long session. Just for those of you joining, to give you a little bit of background about reactors. So reactors are community hubs for developer and startup groups to learn, connect, build on existing skills. So reactors do this by putting together presentations, industry speakers, hands-on workshops, plus meetups and community groups, which are all about emerging technology trends. So reactors are physical event spaces where we usually host these sessions for developer and startup groups, but as you can imagine, given recent circumstances, we're now moving all of this content to an online platform. So hence today's online session. So getting back to today, as I mentioned, it is 1 hour long. You're more than welcome to ask any questions you have throughout. We'll make sure they're answered by the end of the hour. And this session is being recorded. So once we've finished with today, I will be putting it on our YouTube channel, which will be live within about 48 hours. So once I have that link, I'll share it on the meetup group. Okay, so without going any further, I will allow John to take over and introduce today's session. Thanks, John.
So at Wolfram Research, we are both makers of AI and also users of it. And so what I'm going to talk about today is my personal experience of leading our technical services team and the kind of conversations I have with customers when we implement AI solutions for them. If we have enough time in the 45 minutes I intend to speak for, then I'm going to walk through uses of AI, managing bias, validation, explainability, decision-making, and if we have time, ethical issues. So let's start with, what do we mean by AI? Well, for me, there's no intelligence in artificial intelligence. All we're talking about when we're talking about AI is building a model with predictive power. So, as a toy example, imagine we've collected distances traveled on various journeys over time. As a human, we are then able to look at this data and impose a model in our minds and say, this looks kind of like a straight line. And we might play around with what that straight line is. And then we look at the points on this line and say that we can make some prediction from those. And there's an implicit assumption there that our past experience of data tells us something about future behavior, that after 0.7 hours, I might expect to be at a distance of 1 along this journey. And all AI is doing that in an automated way to optimize the values of the model. And we mustn't forget that even when the model becomes so complex and handles such complex data that it appears to be doing something intelligent, in the end, all it's doing is applying a model to make a prediction. And just like these very simple models, there is a lot of supposition in whether that means anything. So it's worth thinking briefly about the way that actually gets applied in practice when we are talking about complex data that's doing much more interesting things than my straight line. And there's several different classes of things that are typically done. One is classification, which is typically a what kind of data is this? So that could be some abstract data, or it could be something like a photograph here where it's trying to predict what kind of face I'm showing, neutral or happy or anger, whatever. It's putting things into classes, and there's lots of different ways one might do that. Prediction, you're trying to come up with a number, but you've got to remember as well that it's not always the number you're interested in. It might be the context of that. So for example, trying to predict the RGB values in this black and white image, that's just a number prediction. It's just the context means we don't think about it as numbers. And then other areas are the kind of what happens next, sequence prediction, clustering and finding groups within data, and various things that seem to be a little bit more creative, but in fact all they're doing is synthesizing data to a pattern. So I could take an image from my webcam here and restyle that so it looks like a Van Gogh painting. It's not, there's no creativity, it's simply looking for a pattern and applying a pattern. But all of those methods have an Achilles heel that we have to remember as our sort of start point of thinking about risks of AI, is that machine learning, which is, you know, what I'm going to really use the term machine learning instead of AI as we go forward, since, as I said, I don't really believe in the intelligence aspect, is good when you're data rich and understanding poor. So you have to have decent amounts of data in order to make all of these kind of modern machine learning methods work. Whether that's labeled or unlabeled or kind of generated as part of the process, it requires data richness. And so there's a converse that you always have to ask yourself before you start with an AI type solution, is if you are understanding rich and data poor, then it may not be the right approach. And maybe what you need to do is to do some good old-fashioned modeling and describe the system in terms of the understanding that you already have, and use human intelligence, not AI type intelligence. Now, the first of our sort of biggest risks, once you've got over the question of do we even want to go into a machine learning world, is issues to do with bias. Now, one thing I always try and point out is, in fact, bias is not a bad thing. Data is usually biased, and that's actually, it's the very bias in the data that allows us to make predictions. So good bias is discrimination. You want to be able to tell the difference between that happy face and that angry face, and you're using that past experience from the data in order to discriminate those cases. If you can't discriminate, then the whole thing is pointless. What we have to avoid is what I prefer to think of not so much as bias, but prejudice, which in the end is giving too much weight to limited or unrepresentative data. And that's the cases that we have to avoid. We have to make sure that the data we're using is representative, and that we have enough of it to establish what is typical and what is representative. So having too little, you can't tell. And if you have too much and you collect it badly, then it may not actually represent the real world that you are interested in. So there's several slices to that. One is just purely false information. And that comes in some fairly obvious forms. Unreliable sources. If you get data from a place that is just wrong, then bad data in will give you bad predictions out. More subtly, poor collection techniques are often a source of unreliable data, that you've got to collect in a way that will generate data that is representative. So you've got to really think about how are you choosing the data points that you collect, how you're acquiring those so that they represent the kind of ground truth of the situation you're interested in. And you can, even having collected well, you can do you know, bad things in processing that actually introduce sort of falseness into the information. Doing things like aggregating, you know, you generally never want to throw any information away. That if you start putting people into bins like age 0 to 18 and 18 to 30 and 30 to 50 and so on, you're taking good data and you're injecting new information in that didn't come from the data, that was based on that arbitrary choice you made of where those boundaries were. So those kinds of things, and how you clean data, can introduce false signals that came from your cleaning process or your collection process. Another one that's a little bit more subtle, though, is hostile data. The data itself is out to get you. And the key thing here is that awareness of collection of data changes the behavior of the things that you're looking at. As soon as you look at something and it knows it's being looked at, it can affect the behavior. And particularly whenever there's some kind of incentive. If you set a target based on some value, then it will change the behavior of whether people meet that target. If you attach money to it in any way, there is always an incentive to change the behavior or to misrepresent the data. So there's a couple of kind of examples. This one's a classic one that's well documented, and one more a personal one. Microsoft fell into this trap a few years ago with their Tay chatbot that they advertised as learning from the conversations that it had with people to improve its conversation. And classically, the internet turned on it, and once the joke of treating it, having bad conversations with it hit the internet, then overnight, literally overnight, it was turned into a kind of racist, misogynistic entity because it had been attacked by people from 4chan and other forums that set out for amusement as their incentive to change its behavior in a non-representative way. But aside from big sort of high-profile attacks, actually even much more subtle things are kind of constantly under attack because of incentives. And this is one that comes from my own life. I gamed Ocado for a while to get lots of these nice £45 off offers or and similar. And the attack was very simple. I had two accounts. Account number one was whenever we needed stuff, we would shop with account number one. But account number two only ever shopped when it was offered promotions. I used it once or twice just to establish it, and then it just waited. When it got a promotion, it would shop. When it didn't, it didn't. And so what Ocado learned fairly quickly is that this account was somebody who was very responsive to offers, and so they sent it lots and lots of offers. And so account number one, after a while, didn't have to be used very much. We were constantly shopping on discount. So, here I'm being kind of, I'm being quite directed and intelligent about that attack. But anytime you are kind of, people know that they are being observed, even if it's just out of embarrassment about admitting truths, it can change behavior, and you have to be careful about that changing the intelligence, injecting that bias into the data for good or ill reasons. Another key problem is the way you actually go about and get the data. That as soon as you choose a source of data, there's a bias injected there because you could have taken the data from somewhere else, but you chose where you got it from. So the key thing is that training data must be representative of your target data. It doesn't actually have to represent the world as a whole. If I'm trying to make something that predicts how 18-year-old men will behave, then I only want to collect data from 18-year-old men. It doesn't necessarily represent the world as a whole. In that sense, it's totally biased, but it's biased in the same direction as I intend to apply it. And that's the key thing, is that the data must not necessarily be representative of the world, but it has to be representative of where you're going to apply it. So I've got a toy example here, which is I'm using our Wolfram Language here to do some basic decision tree classification. And I've got some heights here of people. That this person was 1.67 m, was female, and these data points represent men. And I'm just going to quickly build that predictor and then apply it to somebody who's 1.67 and make my prediction. So it's kind of, you can see here, it's not done a very good job. The only data point it had at 1.67 was female, and yet it's made a male prediction out of this. And actually, if we look at how that predictor behaves over different values, then in fact you find that it never gives a majority prediction of female. It only ever hits about 49% at best. And as we get past the 1.67 sample point, it goes to being pretty certain that they're male according to this data. Now, the reason for that is that I've actually inadvertently taught it two things. One is that that women generally are not as tall as men, but I've also taught it that the majority of this world, as far as it can see, are male. Now, again, as I said, if that was representative of the context I want to use it, if it's can we predict the gender of somebody in the male changing rooms at a sports center, then maybe that is actually a really good data set and is kind of representative of my world. But if I actually just want to gain some truth about people as a whole, then this unbalancedness of the data, because maybe I've collected it in a very male environment, means that we're getting very poor predictions, and you have to do some kind of manual effort here to tell it that that the background probabilities, regardless of the data, are 50-50, and now it can take that 1.67 m and make a useful prediction. better still is to collect the data in a way that I don't have to start making manual corrections with human intelligence. Because as soon as you stick human intelligence into it, you're introducing a new kind of bias. Because as soon as you have humans in the loop, as soon as humans have a role in establishing what truth is, they bring with them all of their baggage about what is true in this situation, learned not just from the experiment, but from, from 40 or 50 years of experience of the world. And a particular form of this is that you have to be careful about is proxy measurements. Very often, we want to make some predictions about something, and we don't really have the truth of the something that we want to predict. So we look around for something that is as close as we can get to the thing that we want to predict, and we use that as a proxy. And that kind of relationship between the proxy and the real thing often is subject to our human assumption that they amount to the same thing. As way of an interesting example, there was a controversy for the Pennsylvania Board of Probation where they tried to predict the risk of reoffending. And they created a model that looked at past prisoners that were released and whether they reoffended. And it was accused of being racist, injecting human assumptions from the parole board about which races were likely to reoffend. Now, I don't think I don't know enough about the model's comment on whether it did a good or bad job, and I don't think anyone was ill-intended. But actually, it's already a case of one of these proxy measurements that human assumption assumes is the right measure, because what we're not measuring is whether or not somebody reoffended when we looked at that data, because what we were actually measuring is whether they were reconvicted. And that's not the same thing. You want to measure reoffending, but who knows? Who knows who's committed a crime and who hasn't? And so we find the next best thing, which is this reoffending measure. But actually, if you break the model down, it's not as simple as this idea of did they reoffend or not reoffend. In fact, the pathways, even in this this is obviously a simplified version of the pathways, are reasonably complicated. That on release, it might be that they reoffend or they don't reoffend, but that's not the end of the process. If they reoffend, they might not get convicted because they might get away with it. They might get caught, and if they get caught, they might not get convicted because they aren't prosecuted. Even if they get caught and they're prosecuted, they might not be convicted because they have good defense, or they might end up being convicted. And even those who don't reoffend, there is a risk that they will actually be prosecuted for something they didn't do and end up convicted or not convicted. So already just this choice of a proxy means that we're muddling up reoffending with the likelihood of being caught when you commit a crime, the likelihood of being prosecuted if you do get caught, the likelihood of being convicted if you were prosecuted. And all of those, of course, have humans in the loop within their own systems. And if you accept the argument that the American judicial system has kind of racist assumptions amongst the police force on who they investigate and who they choose to prosecute and juries within the court system, then you can see how the proxies and the reality that you're trying to predict are not the same thing by any means. Now, of course, the best answer is to try and get the thing that you're trying to measure. But after that, you end up, even to correct for those kind of issues, you have to make human assumptions about putting corrections in. So it's very hard to get away from the role of the human. And the most important thing is to be at least aware and consider the role of the human and not ignore that it's there at every step of every decision step you take of where you collected your data and how you collected it and how you processed it and which measures you chose to collect on and so on. Now, another thing that's worth realizing about bias is that inaccurate is not the same thing as biased. It doesn't matter if your data is in fact mostly wrong, if it's kind of randomly wrong. So if you are measuring people, if we do our height example earlier and we don't have a tape measure, and you just kind of look at people and say, well, they look at like they're 1.70 meters, as long as you're as likely to be above and below for all cases, it doesn't really matter whether you're 10, 20 centimeters out on every measure. It only matters if the error is somehow correlated to the things you're looking at. So if you always overestimate the height of men and underestimate the height of women, then you're injecting a a systematic bias there. But random errors are actually quite tolerable as long as you've got enough data. It will average out in the end. But even if you've got biased data, even if I look at people and for some historical personal bias, I assume men are taller than they are and I assume women are shorter than they are, actually for predictions, it's still not bad as long, and the crucial thing here is that you've got to be consistent with your errors. And that means when you apply your model that you've created, you have to inject the same errors into the application as you did into the training, and then it'll still work. So if you send out people with the same assumptions and they type into the model the observed height as they imagine it to be, if their imagination is in line and they have the same kind of biases as the people who collected the training data, then it will still make good predictions from that data. So it's really all about whether or not the errors in your data and the biases in the data are in some way correlated unhelpfully with the signal you're actually trying to measure against, and then that can completely wreck it. Okay, another thing to worry about, and this is obviously from now on a more kind of social PR and legal basis, is that one has to think about bias on particular protected and sensitive classes. So I'm talking things like race and gender and sexual orientation, where there are laws to say that you cannot make decisions based on such facts. And this is again a slightly tricky area, because unfortunately it's not enough to not ask the question. Because even if you don't ask the question that is prohibited by law, you can actually predict the value of the thing that you weren't allowed to ask. And so the information is still in there because it's correlated to the other things you're measuring. And while this is a very cherry-picked data point from confused.com, it's still kind of a useful comparison that in 2016, under EU laws, car insurance was no longer allowed to discriminate based on gender. So in 2012, before that law came in, men were charged on average £27 a year more than women for their car insurance. In 2017, the year after the insurance company stopped asking whether you were male or female, men were charged on average £101 more for their car insurance, because the models that the car insurance companies were using were still picking up that correlated signal. That if you were, a scaffolder driving many miles a year in a sporty car, in a powerful big car, then the chances are you were male. And if you're driving less and you have a job like a midwife and you're driving a smaller car, then you tend to be female. So the data is still there in what you're collecting. And so the underlying signal still comes through. Now, it's not that the insurance companies actually care or were using this kind of data to try and figure out whether you're male or female without asking the question. They actually aren't interested in that fact at all. What they're interested in is the underlying risk. And because intrinsically men actually are a higher insurance risk, in the end, that still comes through the data. Now, I'm not going to answer the question of what you do about it, because one can try and make corrections which are arguably gender biased in their own right, because if you correct for those facts, then you will end up in a situation where a man and a woman with identical risk profiles, the woman will be charged more systematically, because you're saying, oh, well, it's the man is only risky because he's a man, and so we factor that out, and therefore he's actually low risk, even though he's not low risk. So it's a tricky question what to do about it, but don't think that just by not asking the question that you are immune to the risk of either bad PR in the kind of headline case or even prosecution. You have to really delve much more deeply into the question of protected classes than simply not asking the question. In fact, as I said, this was slightly cherry picked. In fact, once it settled down, the before and after long term was somewhat similar than it was before. It didn't get worse, but it didn't get any better because of the underlying intrinsic risk that they're trying to measure. Right, let's move on from bias and talk about validation and decision making. So the question is, can you use your model? You build this model. Is it safe to use, and what decisions can you make from it? Well, one of the things you have to realize with these kind of modern machine learning models is that you basically have to let go of the idea of checking that it works by understanding the model. almost the very point of machine learning is to pick up the mantle where humans can't cope with the complexity anymore. And so generally speaking, when you get into these sort of deep neural network type models, it is extremely hard to understand how they work and whether they are going to do the right thing in all cases. So what you have to fall back on is a much more software engineering approach, which is instead of checking something works by reading millions of lines of code and scratching your chin and thinking about them, what you do is you test it. And the basic principle of validation is, does it work? If the model works, then use it. If it doesn't work, then don't. And so what you have to do is you have to test it. But here's the crucial thing that many people forget, most notably recently Ofqual in its model for how GCSEs and A-levels should work, is you must test the model on different data than used to train it on. You can't simply, as Ofqual did, look at last year's data, come up with a model, and then see if it worked by plugging in last year's data. You've already looked at the answer. It's kind of cheating in the exam to look at the answer and then find out whether you know how to answer the question. And by way of a toy example here, I've got this ludicrously small training set for image identification, where I'm going to say classify, here's a picture of a dog, it's labeled as a dog, and a picture of a cat, and it's labeled a cat. I'm going to use the Wolfram language here to build a classifier and then apply it. And at first glance, it seems to do a wonderful job. It looks at this picture and this picture, and it makes correct predictions. But that's making that classic mistake of testing on the training set. So it knows the answer to those already because it's seen it. The question is, does it generalize? And to know whether it generalizes, you have to give it some training data, so test data that it has never seen before. And we can see here that, in fact, it isn't a very good model at all. It just happens to be able to handle the cases it saw. It hasn't learned enough to figure out what the general features of dog and cat are. Maybe it would need dozens, maybe it would need thousands of images before it could do that reliably. But we could fool ourselves into thinking that it works if we don't separate out test and training. And it's a bit unfortunate because you will always get the best model by using as much data as you have for the training, but then you have nothing left to test with. So we always need to hold back some decent amount. It depends how much data you've got, but typically 10% of your data might be held back for testing purposes to measure whether the model works. Now, here's another issue that we have to worry about, which is actually summed up in that word generalize that I said about the cats and dogs. Not only do we need to generalize in the sense that we can work with cases that we haven't seen, but we have to generalize in the sense that we have to separate out some underlying essence of the truth of what we're looking at from the noise. So if we go back to my travel example here, we've got our nice model here for a straight line. We could change the model and make it richer and get a maybe even better fit to that data. And maybe this is a kind of better generalization of that data than the straight line, because it certainly seems to predict closer to the data than when I forced everything into a straight line. And we can make richer and richer models that do a better and better job of matching the data that we have. But if you overdo that process, and let's turn this the quality of the flexibility of this model up, eventually something crazy starts happening. And if I go really far up this route, so really high order fit, you can see that in a sense it's now a perfect model that goes through every single point. So every point we've seen can be accurately predicted by the model. But in terms of generalizing what the prediction would be for some unseen places, it's hopelessly wrong. It's now shooting off to some massive number, and it's giving utterly crazy predictions that as a human we would think, well, that's just gone completely wrong. And this is something that's called overfitting, where we are no longer now fitting to the essence or underlying truth that the longer we wait, the further the car will have traveled. But in fact, it's trying to fit all this noise here that the reason why this car had gone further than this car was probably some random event like a traffic light that it got stuck at, or a bit of roadworks that was only there on that one day it was collected. And those random events are not the underlying essence of the model. They are things that will never reoccur. They're effectively random. And if we try and fit to the randomness, then we'll end up trying to predict something that's completely unpredictable. So one has to be careful about making sure that one doesn't give models that overfit, and there's technical solutions to that, which I won't go into in this talk, but the key thing here is that that has to get picked up by the validation process, where by seeing cases that were not in the training data, it gives us a chance of picking up those crazy artificial stupidity type predictions because we've overfitted, and it gives us a chance to know that we're going wrong and we need to do something about the overfitting, or gather more data to learn better what's going on. Now, another thing to realize about measuring your success is that that there is more than simply does it work. That's the first thing we care about, is does it generally work? But actually we have to think about how it fails when it fails. So when it works, that's great. The question, but one also wants to understand, is there a particular pattern to its failure and successes? So by way of an example here, I'm doing some machine learning. I've got a neural network, classic LearNet, trained on character data. So these are little images of characters, and it's making a prediction about what those characters are, to make them actually into numbers so that we could do some calculation with them. So in good practice style, I've got some some test data here that was not in the original training set for the training of this data, and that contains, as you might expect, some examples that that it hasn't seen, along with their truth value. So obviously, if we're going to test whether it works, we need to know what truth is, remembering, of course, that truth is potentially biased according to how I established it, but I think these look pretty safe. The human who has decided what these letters are has done a good job. So here's the headline, that is the thing one usually cares about, is 98% accurate. So it's just counted out of all the cases in the test data, how many it got right and how many it got wrong. But one wants to think about things in a slightly more multidimensional way. And this is, let's see if I can just make this a bit big on screen. Okay, stretch it that way. I'll say the fonts are a bit small here, but what we're seeing here is what's called a confusion matrix. And what it's showing is the actual values up the side, 0 through to 9, and the predicted values 0 through to 9 on the top. So in a perfect model, everything would lie on the diagonal, because anything that was a 0 should be predicted as 0. But we can now start seeing some of the patterns here, that actually the biggest case of incorrectness was 4s being predicted as 9s. So we had 16 cases of that in this training set, and the next worst case being 11 2s that were predicted as 7s. So we can start seeing now, when you think about it in a multidimensional way, that we have two very strong cases of false predictions. And actually, there's two ways one wants to think about some of these rates: is the false positive and the false negative. The when was something actually a 9, but we couldn't find out that it was a 9, so that's the sum of all of these boxes here, versus the false positive when we said it was a 9 when it wasn't, which is the sum of all of the boxes in the column. And so we can measure those things as well for different kinds of data points. So here's the false positive rate, and we can see the false positives are much higher on 5s, 7s, and 9s. And the false negatives are actually much higher on 2s, 4s, and 6s. So we need that kind of information to start asking the questions that we need for decision making of, is this safe to use? Because there are going to be costs and benefits to everything we get right and everything we get wrong in this. Let's skip over how numbers work. Now I'll come back to that in a moment, but I want to say one more thing about validation, which is that you can do everything right, make a great model, validate it, see that it works brilliantly. It does not mean that it will stay brilliant. So one of the things you need to think about is, does the world change? And there's a couple of ways in which the world changes. One is just fashion and progress. So you might be able to predict what everyone will want to buy in a clothing shop today, but that model might not work in a year's time when the whole fashion scene has changed and suddenly your clothes look incredibly dated. Likewise, things that are kind of technological progress will change. But the other one to realize is, back to this sort of idea of hostile data, is that if you are in a competitive environment, then your predictions are there to help you win. But that means that somebody out there is losing because of your predictions, and they will react to that. So, a classic example would be creating a trading algorithm for the markets. I might be able to come up with a model that, and lots of people are trying, but let's say I succeeded and came up with a model that was guaranteed to make me lots and lots of money in trading shares. Now, what would happen, of course, is I would get very quickly very rich, but everyone else I'm trading against would be losing money, and they don't like losing money, so they will change their behavior. Now, they may not know what I'm doing, and they may be looking at what I'm doing and trying to use that to predict me and then outmaneuver me, but at the very least, they're going to want to change the way they're behaving in order to stop losing money, even if they don't understand why. So my model that was based on how they were going to behave is now no longer valid, because as soon as they start losing money, then they change their behavior under that pressure. But so we've got our model, we've validated and measured its predictions. Let's think about how we actually make some decisions on this. So one of the key things is to take that information about where it goes wrong and weigh that up against the benefits of being right. And at the very simple level, one has to just trade wins against losses. So that's very contextual. If I want to come up with something that will predict which will be your favorite flowers to have in a bunch of flowers for a florist, based on something about your profile, even if it's 1% better than stuffing flowers into the bouquet at random, that's pretty good. You might as well use it, because it will be better than it was. And what's the harm in getting it wrong? You'll be no worse off than you were. So maybe a 51% predictor is actually good enough for that scenario. Put that in the context of a self-drive car. A 51% predictor would be an utter disaster, that you only had a 51% chance of making the right decision at every junction you came to. In that kind of context, because the cost of being wrong is a death, and the cost of being right is getting to work 30 seconds faster, then your trade-off of when you are confident enough to make a decision is massively different than when your opportunity for being right is to be a pound better off, and your opportunity cost of being wrong is pennies, in which case you should take every slice of advantage you can get. But one thing that people ask me, so will self-drive cars kill people, and what can we do to stop it? And I always answer that by saying you're asking the wrong question. Self-drive cars will kill people, and that is not intrinsically a reason not to have self-drive cars. Now, it's going to be very sad for the person who gets killed, but the key question, the real question about whether we should move ahead with that kind of technology is it better than the alternatives? If self-drive cars kill fewer people than letting human-driven cars, then they are a good thing. It's a difficult conversation to have with somebody who's been killed by the self-drive car, because you're not having to have the same conversation with somebody who was killed by a human, who is presumably somebody different and that doesn't know of the benefit that they got. But in all of these things, we need to think about what are we moving from, and is it better than that? And very often what we're moving from is humans. So it's worth thinking for a moment about humans. Humans have some intrinsic weaknesses. They are emotional, and they carry a lot of history around with them. So, when you have an algorithm for deciding whether to give somebody a loan, when you've got a human bank manager who's looking at that person, it's very hard for them to forget that this person reminded them of somebody who bullied them at school. and they have this gut feeling, which they aren't quite sure where it comes from, that this person is a bad risk to lend money to, and they decline them. Then there's much more practical things that, even if you can't improve on the human in terms of the performance of the model, the fact that it can be fast and can process thousands of examples a second compared to a human doing, one a minute, or depending on the complexity, slower or slightly faster, and that humans get tired if you ask them to do that over and over again, you don't need your model to actually be a better predictor for it before it becomes useful. And you have to look at, with the issue of fatigue, not just against what is the human capable of, but what does the human deliver in practice. So if you take people who are looking at cancer microscope images to decide diagnosis, they may be very good at it, but actually if you put that person on that job 8 hours a day, they're going to get tired and they're going to make mistakes. So you have to look at the average performance over their kind of whole working week, not just sit them down in a test for 30 minutes and say, did they outperform the computer? You have to look at whether they outperform the computer in the long run, or spend the money to give them a 10-minute working week. But of course, humans also have strengths, and one of those is emotion and history. That it is that background history, the 40 years of training data and our emotional intelligence that stops us making the utter stupid mistakes that that AI models can do, because we're fairly quick to go, well, hang on, that's crazy, when a model tells us that to do something that seems completely irrational. So, you know, we are much worse at being systematically slightly better, but we are much better at not being occasionally terrible. And part of that is adaptability, that when you are outside of the experience space, and again, if you think about, if we go back to my model here, what machine learning methods generally are fairly good where you're within experience data. What happens when you extrapolate and go beyond data that has ever been experienced? Humans are much better at. They're able to kind of use their intelligence to say, well, actually, in this case, cars traveling on a journey, that's probably the model will continue as seen, but maybe only for about 8 hours, because that's the length of time that humans can last before they get tired. And computers aren't very good at that kind of adapting outside of the space. Okay, I'm running short of time, so I'm going to skip forward a little bit and talk about another key issue that a lot of people get confused about, which is prediction versus control, which in essence comes down to correlation versus cause. That sometimes we want to make a model that will simply predict something. What's going to happen next? What kind of thing was this that we gathered data on? That's purely a prediction. Sometimes we want to use it for control. We want to make something happen. If I do this, I will get a better outcome. And one has to be very careful about those two things, because one can get muddled about this cause versus correlation. We're very good at telling ourselves stories. So here's the typical scenario, that you have some observation, that we observe that after event A happened, event B happened. And so we naturally form an explanation that, you know, the typical explanation is A caused B. But there are actually multiple explanations. Actually, there's quite a lot of them, but here's the two most obvious ones. One is that even though you observed them in that order, B was the thing that caused A, in which case changing A is not going to have any effect on B. And the other possibility is that neither is affecting either at all, that in fact there's some third causal reason that's driving both of those. And again, changing A will not change B unless it is explanation A, in which case you can control A to get the result B. So here's a kind of fun example, which is true, that if you observe whether people have beards or not, you can predict with some small correlation whether they're more likely to crash the car. Now, of course, the real causality for this is that those are both things that are correlated with being male, and because, as we've discussed, male driving patterns tend to be higher risk. Being male causes more car crashes, and being male is correlated with having beards. But if you don't think about that causality and leap to the conclusion that that the observation causes the outcome, then the obvious control is that we can improve road safety by shaving everyone. Now, of course, the answer to that is that one has to do your modeling based. If you want to control things, you have to train by controlling the observations. You have to drive the experiment, not just go out into the wild and observe it. If it's just correlation, if it's just prediction you want, then you can just observe data in the wild. So in this case, if we want to have some modeling on whether or not we should shave people in order to improve car crashes, we must do the experiment. We must take a whole bunch of people with and without beards and shave some of them and not shave some of them and observe the result. We're then driving this bearded parameter and then observing the driven behavior. And I think probably fairly quickly we would see the correlation evaporate when we start driving the data. So be careful, do not assume you can control in a driven way if you've simply collected observed data. Okay, let's talk for a moment about explainability. Really, the short answer on this is that it's rather difficult. People are always asking for explainable AI, but actually it's somewhat in conflict with having the most powerful techniques. Because in the end, what these models are doing, the more modern high dimensional models, is they're seeking out an abstraction. They're looking for features that they can explain the model in terms of. Now, we come pre-programmed with features. If we went back to the cat and dog example, because of our long human intelligence history and conversation with each other, we've developed a language for describing things around us. And that's the abstraction that we would use to explain to somebody that's a dog because it's got bigger ears, because it wags its tail more, because the cat has a pointy face, or whatever these features are. Those descriptions are an abstraction. If you went to a world where people had never seen animals, they would have no words for those things. And a person might still be able to, after looking at cats and dogs, start spotting that there was a pattern, but they wouldn't say big ears because they wouldn't know what ears were, and they would maybe not even know what big was. So the language they would use would be something you wouldn't understand. And that's exactly what's going on in most neural network type models, is that it's inventing its own language on the fly. And it's saying this is a cat because it's got a big feature, but that feature might be something that we'd never have a word for, like some kind of zigzaggy splodginess, or maybe it's the browny fuzziness of the upper right and bottom left areas of the image, something that seems irrelevant to us but has worked. But it means that even if you delve into these models to get these abstractions out, the chances are you are incapable of understanding them. So typically, unless you're going to use much more basic techniques, one has to think about explainability more in terms of sensitivity. Another quick example here from the Wolfram Language. I'm going to build a model from the passenger list of the Titanic to predict whether I would have lived or died if I traveled on it. So it's come up with a model, and I would clearly travel first class. I'm 50 and male, and it produces this model that says I'm 68% likely to die. Now, why is that? Well, the sensitivity analysis says that let's compare what if we tweaked these different parameters to see which one has the biggest effect. So I've written a bit of code here that just says, find the probability that I would have died given some new passenger settings compared to the probability that I would have died given who I actually am. And now we can start playing around with the model and saying, well, what happens if I traveled in second class? We'd see there's an 18% shift in the probability of me dying. We can ask what happens if I was 5 years younger? Well, then that would change the probability by 3%, and likewise 5 years older by 3%, and if I was female by 53%. So we can conclude that on the strongest influence here was my gender. The second strongest influence was the class I traveled in, and my age wasn't too relevant. But the key thing to understand about this kind of sensitivity analysis is that it's very specific to the design point that I'm looking at for a first-class 50-year-old male. It's not a general statement that gender was the most important factor followed by class. It might be that if we look at a 15-year-old first-class female, that actually it was the age that mattered most, and maybe the difference between 15 and 20 is a much bigger difference than a 15-year-old traveling in first or second class. So one has to think about sensitivity around the specific case you're looking at. You can only think about these things as general statements if you have a completely linear model where these things are independent of each other, and the proper interesting models are not like that. So the main thing that one can actually do about explainability is really just explain how you got to where you are. And this is just about auditability and reproducibility, that you've got to track everything, because at some point when things go wrong, you're going to ask where they went wrong. And at that point you can analyze it, but only if you've collected everything along the way. How did you collect the data? You've got to hold on to how did you split the training and the test data. You've got to hold on to what were the assumptions you injected, what was the model, and what was the trained model, and how did you validate it. If you've got all of those things, then you can audit and check the reproducibility and find out where things went wrong, or show that that there was nothing kind of untoward about the way you went about it. But in the end, you're only explaining by trying it on different things. And to revisit my question from earlier, this all might seem a bit bleak for machine learning, but I raised the question again of better than humans, because we assume that humans are good at explaining, because when you ask a human, why did you do this, they can tell you an entire story about their decision process. But actually, even that on humans isn't as good as it seems, because basically, first of all, humans don't quite understand their own decision-making process. If there was an emotional reason because the person reminded you of somebody at school when you asked whether to give them a loan somebody you didn't like, you're probably not going to realize that's the reason. You will say, oh, they just didn't seem right. There was something dodgy about their story. And you can't quite put your fingers on sometimes, particularly on borderline cases, why you made decisions. And sometimes humans just lie, that when you say, why did you do this? They make excuses because they're covering up the fact that they didn't think about it at all, or that there was some dodgy reason that was behind the thing, and they will come up with a story for why it was rational that they made the decision that they did. So while we tell good stories, they aren't necessarily as particularly good for explanation. Now I'm a bit over time, so I'm afraid I'm going to skip through some ethical issues and just leave you with the final ethical issue, which is to think about not abdicating responsibility. And if we look back at the kind of pros and cons through, one needs to assign strengths where tasks where the strength is. So in a good AI process, the human's job is, there's still, even though it's kind of artificial machine intelligence, the machine can only, and for the foreseeable future, can only really do a very small part of the entire workflow. It's the human job to think about, how do we get the data? Where does it come from? Is it good? Do I understand the data? Do I understand the gathering process? Do I understand all of the biases and what the outcomes are, what the causations are? These are all human things that you can't abdicate to, great, I've got a black box computer that can make decisions for me. And we still need to decide on the decision-making criteria. Whatever the prediction says, it's a human job to decide to take the computer's advice and when to do this and when not. It's the computer's job to make predictions, and it's the computer's job to apply the decision rules that the computer came up with, because that's where the real benefit comes from, industrializing decision making so that it can be fast, consistent, trackable, reproducible, and all of those great things that computers give us. And it's still a human's job to scratch your chin at the end and go, is it doing a good job? To do validation, to think about the outcomes that and what they really mean on both an ethical and practical and PR level. Even if you've got that self-drive car that is 100 times better than humans at not killing people, if it always chooses to kill 10-year-old girls when it's faced in a crash situation out of the people it could run into, that's going to play very badly in a PR world and maybe unethical. It's certainly, if you're a 12-year-old girl, you're not going to like it at all. So the issues of whether or not we like the decisions of AI are very subtle and very human oriented, and it's our job to make sure that we still do all of those things. And if you're involved in a project that's going down this direction, I would be happy to offer our technical services team to have those kind of conversations with you, or indeed to implement machine learning methods and do the data science for you. Please get in touch. But we have a little bit of time left now, about 10 minutes to take some questions. And you can download the slides that I've been using here to follow through and see the bits that I missed off this URL that's on screen now. So thank you very much, everyone, for listening, and give me a moment here to switch to the question panel and see what questions we have. Okay, so at the moment there's thoughts on SHAP and using that to form those general statements on key indicators, features for your model. If one is interested, okay, so there's a couple of things I want to say about sort of feature generation that can go a little bit further than I went before. So one is that the human can actually play a role in this. If you know what good features are, then actually you can do a lot to shape the data to accentuate the features, and that will accelerate, particularly if you've got small data sets, injecting the features that you think, if you had a good measurer of ear size from images, you could actually extract that out using that human intelligence model and inject that number back into the machine learning model in order to accelerate its ability to tell the difference between cats and dogs in that example. More practically, one often does things like eliminating things that one knows don't matter. If you are doing computer vision and you know that all that matters is shape, then doing things like removing color information from the image actually might accelerate the machine learning towards the shapes of the image contents without it being distracted by whether they are red or blue in trying to decide whether that's a useful feature. And things like in text analysis, there's quite a lot one can do there with doing things like deleting stop words like the and that just litter the text, doing things like dropping case because maybe that we decide that what matters is the words, not whether they're capitalized. It's doing things like removing umlauts and other kind of diacritics. So there's a lot that can be done in terms of cleaning up your data in order to eliminate potentially distracting signals or to accentuate signals that we really think are important. But again, of course, you have to be careful about injecting things that are part of a human assumption. Another thing you can do, when there are these kind of internal models being built, you can actually get in there and see them. So let's do an example here. If I do a model of, let's get a network, which is, I'm going to download an image identification model. Let's see, whoops. Right, so I'm going to download a big neural network here for identifying images. It's got a couple of hundred layers in it. And the idea is that you can do net of, and if I just get an image from Google here, so I'm just opening Google Images on a browser here, and I'm going to look up a picture of a tiger and copy that in. Copy image, right. Let's see if it can make a prediction of a tiger. Right, so there we go. So we got, it's taken this picture and it said that looks like a tiger. So we can reach into this to understand what's going on. We can look at the convolution layers within this and turn them into images, so we can see a picture of the actual convolutions being applied, or we could do things like, let's take the output, only the first part of that, first two layers of that network, and turn those into images. And what we're seeing here is the output of the second layer of the network. So we're seeing that whatever neuron number 1, 2, 3, 4, 5, 6, 7, 8, 9 layer, neuron number 10, convolution number 10 rather, seems to have died out. Whatever features it was looking for don't seem to be present in this image, whereas number 2 seems to have done a very good job at highlighting vertical stripes. So maybe that's a feature that it's picking out. So one can do this stuff, but it is a little bit like looking at into a fire and imagining you see the fairies. That I do feel like anyone who says they really understand how a deep neural network works are either being very approximate or lying. Yeah, so I slightly oversimplified the off-qual issue. I mean, there was a lot that off-qual did wrong. I just happened to notice that they also made this mistake of essentially testing on the training set. Yes, we had a good debate here about if we'd done the data science for off-qual, how we would have gone about it, and had some nice ideas, but so we were never asked for any advice, as you can imagine. Okay, question about the Wolfram language, which I've been using to drive the examples here. How difficult is the Wolfram language to learn and develop in? Also, is it scalable and easy to integrate? It's a somewhat different language than a lot. It's got all the basic paradigms you would expect from a procedural or functional language, although it's fundamentally got symbolic data types, which it makes it feel a little weird for your first 2 or 3 hours, but in the end, it's an incredibly consistent language that's very well documented. So when we train people, we usually get them started in a day, and when I employ people, they're usually productive after a few days of playing around with the language. Just don't fall into the mistake of thinking you have to learn the whole language, because we've taken the approach of having a big language with several thousand primitives rather than the kind of the standard language approach of having a small language and then lots of libraries. No one ever knows the whole thing. And in terms of scalable, actually for the machine learning, it's using MXNet as a backend, so it scales perfectly well. And integration, there is there is things like integration to C, Java, .NET, Python, so you can call it from other languages. It can serve APIs. You can deploy it to the cloud, and we have an engine that you can deploy onto machines. So there's lots to say, but yes, there's no intrinsic limitations in going with Wolfram Language, and lots of benefits that I could talk about for hours, but wasn't supposed to be the point of today's talk. I don't know if the video will be available. Emma from React can comment on that in a moment. Oh, so moderator said, I believe it will be published on YouTube. Okay. Oh, okay. Another question about Wolfram Language. So what are the costs? That's a complicated answer as all of them. There is a free Wolfram Language engine for developers. That is, while you're in development phase, you can just download and help yourself to, and then you only need to license it when it's in production. Full development environments range from sort of £100 for students to a couple of thousand for professionals. There's kind of web production server versions that are somewhat more expensive, but that's the kind of order of magnitude of things in. And then I think you have to talk to sales. There are volume discounts if you're setting a team up and so on. Yes, do feel free to get in touch. And actually, when I put my Twitter on here, I should also give you an email address here, which is, let's take these examples out. If you have questions you want to ask me directly, you can ask me on johnm@wolfram.com. And if you do actually are interested in more sort of salesy things, you can also just go into info@wolfram.com and you'll get routed to some salesperson through that route. But I'd happily take questions first if you have detailed questions that are beyond what I can do live here. Oh yes, and actually for learning, it is worth pointing out here. Let's show you for that. For learning, you can read the full online documentation at reference.wolfram.com. So the whole language is documented here exactly as it is in product. So you can see, if you're going to machine learning, neural networks, and classify, for example, was the function I used. Here's the documentation on how to use classify, so you can get a sense of how the language works before helping yourself to it. It's also worth saying that if you go to Wolfram Cloud, that's another free but somewhat limited way. Oh, I'm logged in, so you can't see the welcome screen, but wolframcloud.com, there is a browser-based version that you can get limited access to free of charge. So just go there and create an account and you can play around with it in a few minutes. But it's not very good on the cloud for machine learning because the free account is limited by CPU time and memory on a single calculation, which, if you're doing simple calculations is fine, but for machine learning, you're always going to be dealing with big data, and the cloud will then reject you in the free account for that. Okay, have I missed any questions? I'm just looking back through. And I guess we are hitting the hour that we were supposed to. So if there are not any final questions, I should probably stop by saying thank you again for your patience listening to my talk. Get in touch if you have questions, and thank you to Emma and everyone at Microsoft React for making this possible and inviting me to speak at it.
Thank you so much, John, for today's session. It's been great having you, and thank you to everyone for attending, for your great questions towards the end, and hopefully you've all had a big takeaway from today's session, and that we will see you at the next Reactor session. So thanks again, and John, it's been great to have you, and yeah, enjoy the rest of your day.
Thanks.